Hello boys and girls. In this video I want to motivate a little more the logical framework underlying, for example, the last video where we talked about the axioms of constructive set theory. So we're going to talk about intuitionistic logic where the law of excluded middle is not adopted as a rule or as an axiom, as a logical tool. And in this framework we are going to prove a statement that is classically the law of excluded middle. So you could say we will prove the law of excluded middle constructively, tongue-in-cheek. What it means is we're just going to prove a statement that shows a sense in which the constructive approach is richer than the classical approach, because in the constructive approach you have in a way more theorems, because classically they all just collapse and become trivially the same. So this phenomenon we're going to observe very directly in some very simple examples as well. And I guess if you understand that example, then you can see how you don't really lose anything if you go into the intuitionistic framework, except that, so to speak, you have less cheat codes in a way. You have the proofs might be harder because you have fewer rules available in a sense. So I talked about this a little bit in the video on non-classical logics in general, and then a year ago I talked about the Curry-Howard correspondence, although that was very coarse, and today I'm going to run some small Python examples. Python example, I could of course choose any language I want. In Python the code is very super concise. It's not typed. Maybe I will redo that with a typed language, but I describe the types. The whole spiel, the whole thing that we're going to evaluate is just these few lines. And before we get into it, let me point to the interpretation that will be underlying the translation from the algorithms to the proofs, or from the types to the propositions. The most explicit general natural language explanation of what we're going to do there is we're going to interpret a proof of a conjunction of two propositions P and Q as a pair of proofs. One proof for P, one proof for Q, and there's these translations for all these logical primitives, but we are also going to need that we're going to interpret a proof of an implication from P to Q of, here there's a function that is the programmatical interpretation, or just a way to entail, to reason from one proof to another, how to use one proof to construct the other proof. The whole interpretation has then a more formal implementation really in typed programming languages, and I'm going also be using some lambdas and some expressions from this sort of their general approach. So the Curry-Howard isomorphism or Curry-Howard correspondence is a little bit younger than this interpretation, but this is all this kind of classical way of thinking about things. And so let's get to the examples. So first we're just going to evaluate these two lines, then the program will hold. So let me just run it first. This is the file called classical law-of-excluded-middle.py. If I run this, then I get a pair. The first entry says that, exclamation mark, and the second entry says this question mark. And so this is what happens here. So I enter this pair. I could also call this here my pair, and I have this switch function which just flips it around. So the first entry with the question marks becomes the second, and the second entry with the exclamation marks becomes the first one. You see, this is the switched around version of that. And how is the code for this simple switch function? Well, we have lambda of p, so p is going to be the pair. He projects out the second coordinate and the first coordinate and just puts them into a new pair in the like turned around manner. I could also maybe write this more Pythonically as switch of p return and then this expression. It would be exactly the same function. So that works the same way. And so the next example will be more clearer, but what we just programmed here is just an implementation that corresponds to the proof that if we have two propositions, A and B, let's say, that the claim that A and B holds together is the same that B and A holds together. Like if I say it's Tuesday today and it's pretty warm outside, then it's the same, logically speaking, as it's pretty warm outside and it's a Tuesday today. So there is this rule that you can commute, you switch around the propositions, and there is also a notion of switching around elements. And so for the first example, this is almost too primitive to see how that generalizes in general, but that's what we're going to discuss next. So I have another function coded up here. The function is called evaluate, and again it takes a pair, but what it does this time, it doesn't put the pairs back in another pair, but it unpacks the second coordinate, and then this is interpreted as a function and applied to the first coordinate, right? So for example, in the first example here, I have a pair where the first entry is LEM, it's a string that says LEM, so this is some string with three characters. And then there is a function, the inbuilt function from Python called length function. And what is going to happen is, if I evaluate this pair, then he takes the second component, this is the length function, and applies it to the first component. And that's why it's an evaluation. That's why I called it evaluate, right? Or similarly, in the second example, the function takes a word and returns the word but appends appends an exclamation mark, and so this will say subscribe exclamation mark. So let's run these examples. Okay, so first the already discussed switch, and then the thing has three characters, then subscribe exclamation mark, and then here we have here we have the value 5 and the function that takes n to n times n, so this is a square function, we get 25. And then we have a more complicated example. The first entry is again the square function, and the second entry is a function of functions that takes any function and evaluates the function at 3 and subtract the value that arises from evaluating the function at 1. So what happens here is it takes the square function, evaluates it at 3, we get 9, then it subtracts from 9 the square function at 1, so in the end we get 8 out of that, right? So in this is the more complicated example where both entries are functions, but you can still evaluate them in the sense that you can evaluate an integral on the function and you get a value out of it, right? This would be another example, and this is basically a version of that. Okay, so the thing is now that the evaluate function is effectively what did I actually? Yeah, it's effectively the logical modus ponens, really, because on the one hand you get some function, something that takes some value to another value. Programmatically, this is really just a function. Logically, in the interpretation we just talked about, this is an implication. And then we have some value, and these work together in the sense that we can plug in the proposition to the implication, and if, for example, if the implication says if it's raining outside, then I will be wet, and if I also have that it's raining outside, then this entails that I'm wet, right? And so here you see the realization of that would be, for example, this example. I have the length function, which takes some string to a number, and I have actually a string, and so I can get to the number. In the Curry-Howard isomorphism, you have there's different types, languages, and different variation in what sense you want to implement that, and you will interpret types of propositions more abstractly, and not necessarily as strings, or as you will not use the type of some numbers that has so many inhabitants. But this example is really just to see the gist of interpreting the entailment as taken forward a value, right? You see the parallel there, and you would, if you have a theorem prover where you actually want to prove propositional logic statements, then you would have your own maybe constraints on the types so that they are properly to be interpreted as propositions. For example, you might say they only have 0 or 1 value, and you, depending on how much information is in your proofs, there are many ways of getting at that. But I suppose the general principle of the Kolmogorov interpretation of functions as proof and the other way around, and pairs as conjunctions of propositions and so on, should be rather clear. Okay, and so let's actually look at these functions if I had used them in a typed language. And in this case, I can actually do that even in Haskell. Maybe I will actually redo it. I did it in Python simply because people know how it looks like and to understand it simply. But so the point is here again I have the switch function that I coded up before, right? Sorry, this should be so. So I called this MP for modus ponens, but this is just a second example there. So the function, if we look it up again, we get the P, we switch around the entries and put them back into a new pair, right? And so here we have the lambda, it takes a P, it returns the pair that I denote with these sharp brackets here. The pi is supposed to be the projection to the right component, the projection to the left component, and the switching around is just that, right? It takes the pair, gets the second entry, puts it in the left entry of the new pair, and this the same thing for this. And so I call this function switch as I did with the Python code, and also I will discuss the type here. So given that we can abstract over the types, so for example the S and T would be types in the example. For example, S and T would both be strings. Then this function which switches the entries of pair around would be of the type S times T to T times S, right? So whatever types these entries were, afterwards they were switched. If they're the same type, then if S and T is the same, then of course we get the same out of it at the end again. S and T, like S times S goes to S times S in this case. But nevertheless, I hope the reading of this expression is clear. And now the second example, for example, the syntax is basically the same again. Now with this application, these brackets are just to separate the function, right? So the right projection of P, this is going to be the function, like for example this function, and this is then taken and applied to whatever the left entry is. And the type of this is therefore the following. We have some C, this is the value, like for example in this case the value 5, in this case the square function, And then we have some function that gets from C to some B. In this case, for example, from integers to integers, or here from functions to integers, like from square function to 8 in this case. And the evaluation like joins them together. You put the C into the C to B, and you get a B out of it. Okay, it's clear, right? And so I have here this eat function, which is really just a special case of the MP function that we had before. So what I have here is that I restrict myself more. I say, okay, the C cannot be any value, but the C now has to be like any value of any type C, but the C has to be now a function of a function space. So I really just replace, if I make a comment here, C is let's say concretized. I'm not sure if that's a word. To A to B, right? If you take this and plug in for C just A to B, we're already abstracting over B, so we have now, this is what I call A, but this is just a quantified type variable. And so, for example, this function would be of this type, right? This would be an instance of the eat function, but the evaluation of the square function at 5 is not of this type, because the value is now not a function. So this is especially this eat function is especially a proper evaluation function for this function eating functions that we have here, right? Okay, and this like interpreted as propositions in logic, in the sense that we discussed before. Everything goes through that we did before, like did until now, right? So for example, constructively, if you have some proposition and some implication, then the result is true. Like my rain and wet example. So this modus ponens application goes through, of course, constructively also. This is very constructive, this function application reading. And in the same sense, this eat function is also valid. So this MP and eat are really the proofs for these statements. Because even if like the principle that is behind them, like the way you actually act, the way the algorithm actually proceeds, is also the logic of the proof. You have two different proofs, and you have one way of turning one proof into another, and you actually apply this procedure to the one proof, and you get a new proof out of it, and that's how you get to this statement. Okay, so here the interpretation. If I have a reason to be, sorry, this was right. I have a reason to believe B, here this result, if both are the case at once. If I have reasons to believe these two things. On the one hand, that A implies B, and on the other hand, that A implying B already implies B, right? So if that is the case, as well as the whole thing here being the case, yeah, then I can use the witness of A to B, plug it in to A to B, and then I have a reason also for B, right? So this is just the logic reading of this statement. Okay, and what we now do is we introduce we can say a logical constant, the turnstile bottom, you can call it, or absurdum. Like the wrong proposition is a logically false proposition. That's one way of reading it. And we introduce just a notation, right? We just say to say that something is false, to say that something is not true, amounts to proving that if we had a reason to believe A, then that would be absurd. So if it would be absurd if I would look myself in the mirror and see I'm a bird, and so that means I'm not a bird. just as a natural language example, right? So if I can show that having a reason to believe A would be absurd, then A is not the case. And you can phrase this in many different ways, but from a standpoint, this is the one standard way of introducing negation. So to proving something is to proving something false amounts to proving that if you would assume it, then you would get to a contradiction, you would get an absurd result. And so if we take our logic constant as a false proposition, and if we have actually some moral constants in our logic, if we have, for example, a logic of natural numbers, then we might actually get around introducing this bottom by simply taking some proposition that we just don't want to have part of our provable statements. For example, if you have natural numbers, you can say 0 equals to 1, and then you can take that as a placeholder for this absurdum, right? You can say, like in the case we speak of a logic that has natural numbers, you can write this here. For example, that would be one way of introducing falsehood. You say some proposition about natural numbers is false if you assume it, you are able to construct a proof of 0 being 1, right? But for now, let's just introduce the negation in this way. Okay, and since this is also just a proposition, a false proposition, this constant, we can plug it in to the EAT proposition that we have already proven, right? Let me delete this here. So if we do that, then this becomes not A, and this becomes not A, right? Because this is just, let me actually do that. We get EAT prime. This is just an example here. Then so sub. This is just a substitution of one particular case because it holds for all B anyway. And now this means not A and not A and not of this, right? So this is really just this here. I might add this for all, although we know what we're talking about. So this is also true, and it's easy to read as well. What does it mean, even constructively, for propositions? The following is the case: that it would be absurd, right? We would get the absurdity. It would be absurd if both are the case at once. That on the one hand, A is absurd, and also that A being absurd is absurd. Right? If that's the case, if we have reasons to believe both, then we can construct actually an absurdity, like a contradiction, by using the proof of this absurdity in constructing the absurdity here, showing that, oh, this is actually absurd, so the whole thing is wrong. And so the proof of this statement is really just the same as this the same as EAT, and which is the same as modus ponens. So I could write, like, if I have a type system where the compiler is clever enough to do the type simplifications, then I can use modus ponens as a proof for that, really, right? So again, this is my like in the modus ponens page, for example, this is my P. Not A is some proposition, like the proposition is A is absurd. The other one is A being absurd leads to an absurdity. If I have these both things, then I am led to an absurdity. Okay, so, and given that, we have this statement, okay? And the point of the video is now that classically, like, if I now have constructively proven the statement, and if I at this point say, okay, from now on I accept classical logic, then I can use classical rules to show that this statement is equivalent with the law of excluded-middle. So in particular, if I have De Morgan's law, so I will not dwell on that too much, but you have the Wikipedia page. This is basically this rule that if you have, if it's not the case that I'm in Spain and I'm in London or Britain, then either of those is not, at least one of them is not the case. Either I'm not in Spain or not in London, right? So there's this logical equivalence. So this law we can only use once we pass to the classical logic, because not all the De Morgan's law implications hold in all directions. I'm not going to dwell on that either. So you can see how you can get to classical proofs in a harder way. There's more like work involved for the proofs because you cannot use the cheat codes. But on the other hand, you also have this constructive procedure at your hand at the end of what you do. To wrap this up, let me just point you to further reading in this direction. So there's the general double negation translation and based on Gödel's work, and you have these translations for various logics. Also, in this case, I just talked about propositional logics. You can also see variants in predicate logics, and then in modal variants and embedding, for example, the intuitionistic case in models for modal setups and so on and so forth. And also, if you're into category theory, the whole spiel with the lambdas, there's this abstract definition of the lambda, the evaluation and what amounts to the lambda abstraction. Okay, so this is a quite short article, but nevertheless, you can see how it works, and then you can check the categories in which it works and where you can do the similar constructions, and then you can kind of see how the computational and the logical and this algebraic, if you will, side go together. And then finally, to really believe how this might translate to more complicated theories, I encourage you to look at this short example in the constructive analysis article on the intermediate value theorem. So there is these 4 sections which are very instructive. At first, they just say what the intermediate theorem analysis say. Then they give one constructive version of it, because the intermediate theorem, as it is here, does not hold constructively. However, there are then statements that amount basically to approximation algorithms, and then you get that in some variant of it, it tells you how to get as close as you want to this, the 0 point, the intermediate value. But then they also speak about another theorem, which is another approach to the same problem as this, but strengthening some conditions. And then finally they point out that if you are in a classical setting, then this condition that you have, this extra condition on the constructive version, is actually void classically. So in reality, once you have proven this constructively, and you say, okay, now I go to the classical setting, then similar to the law of excluded-middle example that we just had, the theorem that you have proven actually reduces, like just by logic, to the classical logic result. So you're actually you cannot prove the intermediate value theorem as stated classically, as formulated classically. It just doesn't hold. But you can find another theorem that you can prove constructively, and then in classical logic, this theorem that you just proven constructively is actually the intermediate theorem, because the condition is just trivially true, the extra condition. Okay, so I hope that made sense. I'm open for comments, and sleep well, I guess.